everyone. My name is Rutuja Magdum. Today, me, Devang, and I are excited to present our research paper on ST2VEC Spatio-Temporal Trajectory Similarity Learning in Road Networks. Okay, so the purpose of our study was spatio-temporal trajectory similarity computation. In this presentation, we will be sharing with you our methodology, findings, and conclusion, as well as some of the limitations and future direction for this research. As we know, the GPS trajectory data is being collected at a large scale, leading the need of trajectory analytics. Trajectory similarity computation is a crucial task in various applications, such as ride sharing, traffic analysis, and social recommendation. Traditional handcrafted distance measures for trajectory similarity computation are associated with high computation cost and are not scalable. To address these issues, a new line of study aims to utilize a neural network to learn trajectory similarities for similarity computation by mapping a trajectory to d-dimensional vectors and then calculating the similarities between trajectories based on their embeddings. Existing similarity learning based trajectory similarity computation approaches to improve the time complexity but do not consider the temporal dimension of trajectories, limiting their efficiency in time-aware scenarios. The spatial similarity oriented trajectory embeddings learn and generate only spatially similar trajectories, making them inefficient for time-aware scenarios. We argue that a general similarity measure should consider both the spatial and the temporal aspects of trajectories, and that time is an essential dimension of spatio-temporal trajectory data and deserves an attention on par with the spatial aspect. In challenges section, this paper proposes a new approach called ST2VEC for learning spatio-temporal trajectory similarity in road network by addressing three challenges. First one is temporal embedding, second is spatio-temporal fusion, and third is model optimization. To achieve this, they use a deep learning techniques such as recurrent neural networks (RNN) and purpose of fusion approach that adapts the varying spatial and temporal weights. The author provides experimental results that shows that ST2VEC outperforms four state-of-art competitors in terms of effectiveness, efficiency, and scalability. In addition, case studies including top K similarity, queuing, and clustering demonstrate a downstream capabilities of ST2VEC. The paper also presents the problem they aim to solve and define road networks and trajectories. And they study a road network constraint trajectory similarity using state-of-art networks aware distance measures. For the next, in the preliminary section, the text defines road networks as directed graph with road vertices and edge sets, and GPS trajectory as time-ordered sequence of sampling points with location and time information. The vertices of the road network represent road interaction or ends, and the edge represented directed road segments between intersection. The trajectory is captured as a sequence of location time tuples from GPS devices. There are definitions for road and trajectory in this research paper. The definition consists of for a road network is modeled as directed graph where G is equal to LE, where L is a set of road vertices and E belongs to an edge set of road segments. The vertex Li is equal to xi comma yi belongs to L models of a road intersection or road end in which xi yi denotes a longitude and latitude of Li respectively, and a edge ELI LJ belongs to a models a directed road segment from Li to LJ. For GPS trajectory T, H is equal to G1 T1, G2 T2 from Gn to Tn, where n is denotes the length of T, and there is a definition for trajectory T, which is given by T is equal to H of G1 T1, G2 T2 from Gn Tn, where n denotes the length of T. Where and there is a definition for trajectory as well. Given a road network G is equal to LE, a trajectory T is directed sequence of M, where M is less than equal to N. Vertices in a G that is T is equal to H of L1 T1, L2 T2 from LM to TM, where Li belongs to capital L is a vertex and Ti is corresponding time. The paper focuses on road network constraint trajectory similarity learning by aligning trajectory points with vertices on the road network. The spatio-temporal similarity between trajectories is defined as a linear combination of spatial and temporal similarity measures, which is the learning target of ST2VEC. The paper explores the state-of-art network Our distance measures including TP, DT, LICRs, and NET ERP to study road network constraint trajectory similarity. The paper proposes using two parameters to control the relative weight and spatial and temporal similarity and the overall similarity. In the problem statement section, the paper has provided problem formulation, alternative solution, and ST2VEC solution. Spatio-temporal similarity learning aims to train a neural network that realizes the function G's by embedding trajectories into low-dimensional vectors that reflect their similarity relation. In alternative solution section, two alternative solutions exist to realize the spatio-temporal trajectory similarity computation. Split the time into discrete time intervals and assign trajectories to different time intervals using sliding window methods. However, this approach is spatially oriented, is coarse-grained, and is suboptimal. The paper considers two approaches to capture the temporal information of trajectories, feeding the time sequence of trajectories to RNNs the same way that location sequence of trajectories are fed to RNNs, and combining the resulting temporal vectors with the spatial vectors to achieve spatio-temporal similarity learning. Okay, now Devang will provide you with the information about ST2VEC approach.
All, I am Devang. As Rutuja explained us all about the problem statement, what are the goals that we're gonna achieve through this study, and what are the preliminaries about the paper. So I will, without wasting the time, I will directly dive deep into the approach. So the author has proposed a representation learning based architecture, which is termed spatio-temporal similarity vectorization, and this is capable of exploiting the fine-grained temporal and spatial information in the trajectories to enable unified spatio-temporal similarity learning. It takes similar and dissimilar pairs of anchors trajectories to construct a input similarity triplet, which can be used or considering both the spatial and temporal dimensions. So as we can see, we have like four main modules for this basic approach. The first module is a temporal modeling module where we are trying to get a temporal sequence embedding, and a spatio modeling module where we are trying to develop a spatio spatio embedding, and later we are trying to fuse them together using a co-attention module so that it can be passed along to our final model for training and analysis. Using this approach, the authors have been able to beat up all the state of art theories, and they have done a great job, and we are excited to go further. So here we are going to discuss about temporal modeling module. This is like a very critical part which is used to achieve temporal representation learning. Here we integrate by designing a time embedding with a temporal sequence embedding to construct a trajectory aware temporal sequence module. At different points at different time points may have like different importance, like rush hour is always different from late night. Thus we further introduce a attention function to enhance the representation of temporal irregularity. In a time embedding phase, this describes a method for embedding a temporal trajectory into a sequence of time vectors using time embedding vectors, which are denoted as t hash and are of size q plus 1 for each time point t in the trajectory. The vector t hash is learned using a set of learnable parameters that are omega and phase shifts ranging from 0 to q. In this equation, the time shift is calculated using periodic activation function, and a cause function helps us capture periodic behavior without the need of feature engineering. So Wi and phi I are the frequency and the phase shift of the cause functions. In the time sequence embedding, this phase describes a method for modeling the temporal dependency of a trajectory using an LSTM model. After embedding each time point using the time embedding vector, the LSTM cell takes this vector and the state of the previous step as input and outputs the state vector of the current step. The LSTM unit exploits the embedding time, the hidden state, and the cell state from the previous step to compute a new hidden state and update the cell state. The final hidden state of the LSTM represents deep temporal trajectory representation and contains all the temporal information of the trajectory. So further we move to our decoupled attention module, which describes how attention mechanisms are used to capture the correlations between trajectory points and improve the effectiveness of model. The proposed self-attention mechanism computes the attention score between time points in the same trajectory by taking a dot product of these two hidden representations and applying a softmax function to obtain the attention weights. The improved state representation is obtained by using a weighted sum of these hidden representations at different and all the time points, and the attention function is parameterized by w1 and w2 and which are learned during the training phase. So that's all. Modeling module is similar to temporal modeling module and consists of the similar three phases: a location embedding, spatial sequence embedding, and a spatial attention. To take into account the underlying spatial dependencies in a road network, the SSM uses graph neural networks. The resulting embedding vector is designed to capture a spatial similarity and can be used for downstream tasks for classification, region classification, and traffic prediction. The location embedding phase has a node to vector which is utilized to capture the co-occurrence of adjacent locations in the road network and to approximate the spatial conditional probability of vertices in its neighborhood. In the spatial sequence embedding phase, the embedded locations are fed to a graph convolution network to obtain locally smooth location embeddings, which spatially adjacent locations tend to be close to latent space. The spatial sequence embedding in this case involves obtaining an initialized location sequence representation, which is then fed into a LSTM model like we did in our temporal modeling module. So in this self-attention mechanism, which is applied to capture different contributions of different location in the learning process, helps to account for the fact that different location points in a trajectory can contribute differently to the similarity computation, with noisy location points and with obvious deviations from other points which can highly influence our computation. Finally, the hidden state of the last step of the LSTM model is used for spatial embedding. There are two methods for combining the spatio and temporal embeddings. One is a separate fusion. This is a technique that is used for embedding spatio-temporal trajectories and involves generating separate embeddings for both of these trajectory components. This is achieved by training two separate LSTM models, one for capturing the temporal information and other for capturing the spatial one. The separate fusion approach can be effective in the spatiotemporal embedding, but it comes with a disadvantage of doubling the number of parameters determined by the model. This can make the training process much slower and more computationally expensive, especially for large set of datasets. So the author suggested a technique of unified fusion which is used to combine temporal and spatial sequence embeddings of the trajectories to obtain a more comprehensive representation of the trajectory. The initial temporal sequence is denoted by t with a time, and initial spatial sequence is denoted by a trajectory of s. A co-attention fusion module is designed to enhance these representation by letting them interact with each other. The transformation of the temporal and spatial features is denoted by a matrix wf, and the interaction between these two representation is calculated using a softmax function. The enhanced temporal and spatial embeddings, the new enhanced temporal and spatial embeddings are denoted by t, the trajectory of t hat and trajectory of spatial hat respectively. These enhanced representation are then fed into a single LSTM architecture to obtain a unified spatio-temporal trajectory embedding. This co-attention fusion module allows the embeddings to interact and learn from each other, resulting in a more comprehensive representation, and can be used in various applications that require analysis of spatio-temporal data such as transportation systems, weather forecasting, and surveillance systems. Training and optimization phase, and this trajectory similarity learning method uses a neural network to learn embeddings that approximate the chosen similarity function. To train the network, representative similarity triplets, a trajectory of anchor, trajectory of positive, and a trajectory of negative, are obtained through selection strategy that randomly selects one of the trajectory as anchor and samples a similar trajectory as its positive and a dissimilar trajectory as its negative. This creates a trade-off between robustness and efficiency. In the modeling phase, a vectorization embeds the triplet of trajectories considering both temporal and spatial aspects. The function f provides the functionality of g, and the spatio-temporal similarities can be computed by L2 norms and the ground truth similarity. The loss function is defined as the weighted sum of some squared errors of similarity triplets which combine the spatial similarity and the temporal similarity into a unified measure. To optimize this training process, the method uses curriculum learning, which involves training easy samples before hard ones. Given a trajectory anchor TA and its k similar and dissimilar ones, we will be starting by training k triplets that can be obtained and ordered from most dissimilar to a anchor triplet. The triples are then fed into the network from easy to hard, which results in faster convergence and higher accuracy. Overall, this is an effective and robust method for trajectory similarity learning that considers both spatial and temporal aspects and uses curriculum learning for optimization.
Hello everyone, I'll walk you through the experimental study and the results from the authors of this paper. Considering the datasets, in their experiments, authors used real-time trajectory datasets of taxi trajectory points from Beijing, Rome, and Xi'an and adopted them from their experiments. Since the experiment was trajectory similarity analytics, they mapped the matching trajectory to the road networks from OpenStreetMap, which led to the transformation of the raw trajectory GPS data into time-ordered vertex sequences according to the definition of trajectory definitions given earlier. As part of the data cleaning, the authors removed the trajectories with less than 10 samples. As far as evaluation matrix and ground truth is concerned, like other trajectory similarity studies for the validation of their solution, the authors of this paper have used top case similarity search at HR at the rate 10, HR at the rate 50, and R10 at the rate 50 as evaluation matrix. Here, HR at the rate K denotes the hitting ratio that captures the degree of overlap between a top K results and the correlation ground truth result, and rk@t is the top T recall for the top K ground truth. For comparison against the ground truths from TP, DETA, LCSRS, and NetERP, they have used the same top K similarity search. The effectiveness of the model is higher where HR@K and RT@K is closer to 1. Competitors or baselines. As one of the goals of this paper is to prove the solution provided by the authors of this paper perform better than so far some of the well-known existing solutions, authors have performed a comparison of the S2VEC results from all the existing similarity learning methods, which are Nutra-J, Tran-J, 2-SIMVEC, T3S, and GTS. For the sake of fairness, authors extended these existing solutions with time control, thus resulting in 12 comparative results that we can see in the table. The TP, DETA, LCRS, and NetERP are 4 trajectory analytics systems. Nutra-J, Trans2SIMVEC, T2S, and GTS are 4 methods to calculate trajectory similarity. Further, authors created 3 categories with window guided baseline, LSTM guided baselines, and TMM guided baselines. In the window guided baselines, trajectories are distributed across the discrete time slots. In LSTM guided baselines, temporal trajectories are directly fed into the LSTM model, and in TMM guided baseline, the temporal trajectory embedding module is integrated. Considering the hyperparameters for S2VEC, authors use the UF strategy as the default, and for all competitor methods, they use the SF strategy as the default. Training, validation, and data sets were split in the ratio of 3:1:6. The default value of lambda was set to 0.5. The spatial and temporal embedding dimensionalities were set to 128. LSTM was configured to 128 hidden layers. The batch size was set to 50. The model was trained using Adam with an initial learning rate of 0.001. The implementation of S2VEC was achieved in Python and PyTorch. This slide represents the effectiveness of the top case similarity queries for all the 12 baseline approaches. The tables in the slide list the results of the run for the competitor models and the author's model. Table 1 is from T-Drive Beijing dataset, Table 2 is from Rome, and the third table is from the Xi'an datasets. To demonstrate the model, they conducted top case similarity queries and compared the performance of ST2VEC and all 12 baseline approaches. We can observe that the TMM guided baseline models from the authors of the paper significantly outperforms the window guided and LSTM guided baselines, indicating that the proposed temporal trajectory embedding modules is effective. The second observation is that in the same category, GTS and S2VEC outperforms the other methods on all metrics. The third observation is that ST2VEC achieves substantially better accuracy than GTS on all distance measure and all datasets. This reflects the fact that GTS target POI based trajectory similarity computation that disregards the actual travel path between the adjacent POIs. Given a target trajectory, the trajectory with the same neighboring POIs constitute its return as its top case similarity querying results, although the movement paths of such trajectory can be very different from that of the target trajectory. In contrast, ST2VEC is designed for fine-grained trajectory similarity learning and considers both location and travel paths between adjacent sample locations. Consequently, ST2VEC is capable of better similarity learning performance. The histograms in the slide show the efficiency of the model in terms of model training and all-on computing. The histogram is drawn on T-Drive and ROM datasets for training and computing. The authors have kept the scale of the y-axis logarithmic due to the significant performance differences. As can be seen, ST2VEC has good performance for both training and computing. Considering the results for the T-Drive, as an example, during the training phase, ST2VEC finishes each epoch within 40 seconds and runs 2 times faster than Nutra-J, 3T3S and GTS, and 5 times faster than Traz2SIMVEC. In terms of similarity computation, the paper measures the total running time of each method on the test data. Here ST2VEC also exhibits superior performance and is 20 times faster than Rutuja and T3S and 2 times faster than Trace2Sim and GTS. Next, we explore model scalability when varying the number of trajectories from 10K to 200K. Table shows the results when learning 4 distance measures on T-Drive and ROM. As we can observe, ST2VEC offers the best scalability for learning based trajectory similarity computation due to 3 observations. First, the running time increases with cardinality. Second, ST2VEC offers substantial performance improvements over the existing methods. Third, the performance of ST2VEC is affected less by an increase in cardinality than the 4 baselines. So consequently, ST2VEC is capable of large-scale trajectory similarity computations. Further, we evaluate the sensitivity of ST2VEC to assess its robustness. Specifically, we consider the effect on the model performance of the training data size, the number of triplets n constructed for each trajectory, and the spatio-temporal weight lambda. First, we investigate the effect of number of training trajectories on the performance of ST2VEC. Figure shows the similarity learning performance for the 4 measures when varying the training data size from 10K to 200K. We can observe that ST2VEC exhibits stable performance. Second, we investigate model robustness when varying K for constructing training samples. Here, authors randomly sample 10K trajectory from T-Drive. Then for each trajectory, they get its 1, 3, 6, 15, and 30 most similar or dissimilar trajectories to construct similarity triplets. In the plots, we observe HR at the rate 10, HR8 at the 50, and R10 at the rate 50 all increase slightly, which offers evidence that ST2VEC can achieve good performance even with the limited training samples. Finally, when performing a sensitivity analysis of the spatio-temporal weight lambda, for lambda is equal to 1, only the spatial domain is considered, and when lambda is equal to 0, a similar computation considers the temporal domain only. Plots at the bottom of the slide shows that HR at the rate 10, HR at the rate 50, and R10 at the rate 50 performance are stable across different settings of lambda, indicating that ST2VEC works well with different lambda preferences. To study the effect of the attention mechanism on the performance, author remove it from ST2VEC and call the resulting model ST2VEC no attention. The HR at the rate 50 results on T drive are shown in the histograms, indicating that the spatial and temporal attention mechanisms are effective. Taking TP as an example, ST2VEC improves HR at the rate 50 over ST2VEC no attention from 0.51 to 0.58. Second, to evaluate the effect of fusion approach on the model performance, the authors train ST2VEC using separate fusion and unified fusion. The histogram shows the ST2VEC using unified fusion achieves similar effectiveness to that using separate fusion. However, the ST2VEC unified fusion achieves fast model convergence than the ST2VEC separate fusion. Finally, to evaluate the effect of curriculum learning on the model performance, author considers all 4 distances. The plots shows that the learning process guided by the curriculum learning achieves faster convergence and higher computational than the random batch learning. As a follow-up approach to the analysis of ST2VEC, authors consider similarity computation using the ST2VEC based method and a traditional pairwise based method. Table reports the average time cost to perform a top 50 spatio-temporal similarity search for each query trajectory with different data sizes, comparing the query efficiency under ST2VEC and non-learning. As can be observed, ST2VEC achieves 200 to 400 times speeds up over the non-learning based methods. In case study, authors performed trajectory top K querying and clustering using T-Drive to examine the capabilities of ST2VEC intuitively. The figure plots different trajectories and shows that the trajectories returned by ST2VEC match the ground truth trajectories very well. Exploring the effectiveness of ST2VEC using DBS scan clustering when fixing the parameters mean PTS at 10, authors use TP and compare the clustering results generated by the ground truth and embedding based distances. As shown in the figure, the number of clusters in the two results share similar trend as epsilon grows, meaning that the ST2VEC also works well for clustering analytics. In conclusion, the authors proposed ST2VEC, a representation learning based architecture for spatio-temporal similarity learning in road networks while enabling a range of trajectory measures. Extensive experiments using three real data sets confirm ST2VEC is capable of improved higher effectiveness, efficiency, and scalability than state-of-art methods. Also, similarity-based case studies of top-K querying and clustering demonstrates the potential of ST2VEC for downstream analytics. In the future, they propose it is of interest to integrate ST2VEC into spatial database management, thus enabling more types of trajectory analysis.